because I'm tired of these guys, as you probably are, of finding a max and a min. And once we got this done, that's as much time as I can give you on 14.7. And then we'll move on to 14.8, where I'm going to show you how to solve the same problems, but using a totally different technique, completely different really, called Laplace transforms. And they are so cool. Much easier, in my opinion, as well. So here's the puzzle. There are 3 questions, pretty much the same. Find the shortest distance from a surface to a point. And questions 15, 16, and 17 are themes on this. So we want to let D be the distance from the point 0 to 1 and this plane. So can you imagine this is a plane in 3D space, and this is the point P. And this plane happens to have equation x take away 2y plus 3z equals 9. And you just have to trust me right now, that's what the equation of a plane looks like. But if you remember back to Calc 3, isn't that what the equation of a plane looks like, right? And now if you want to find the shortest distance, can you imagine a little invisible dotted line would meet this plane P at a point Q, and that is the shortest distance, right? Now, I could probably do a visual on this that might actually work. Can you imagine this piece of cardboard? Right? Goes like this. Tip of my pen is P. Wouldn't you do a line straight to the plane perpendicular to the plane, right? From the point here, right down there. And the length of that pen, wouldn't that be the shortest distance? If I keep the tip of the pen, would you agree that that's a longer distance this way? And it's a longer distance that way, but there's a kind of sweet point, shortest distance. So every one of these questions, there's going to be at least one, if not more than one point that is closer to all the others. And that question becomes one of these max and min problems, in this case, a min problem. And the equation of the plane, which is this guy, is actually the constraint function. And the function that we're trying to minimize, we're being told, is d squared. So I'm now going to set up this problem and try and solve it. Okay. So that guy I'm going to call XYZ. So Q is going to be called XYZ. Then D is the distance from the point P, which has coordinates 0, 2, 1, and Q, right? So the distance PQ. Well, we know how to find the distance. It's the difference in the X coordinates squared, plus the difference in the Y coordinates squared, plus the difference in the Z coordinates squared. So far, so good?
Mr. Robertson, did you say the constraint function is the same as the equation of the plane?
Yes.
So then is the equation of the plane x minus 2y
Ooh,
plus 2y?
I don't know. Let me check. It's minus. That's me transferring wrong. I'm glad you caught it now. It wouldn't really matter. I would just be finding the distance from this plane to the point rather than the one that they were given. But it's important we be consistent. So if I asked you to find d squared, wouldn't it get rid of the square root? And that guy would become x squared. And this guy would become y take away 2 squared. And this guy would be z take away 1 squared. Everything so far so good? Right, so I'm now going to change this question just a little bit and make it more like all the others we were doing yesterday, or at least the ones we were doing yesterday. So I have a function f of xy. He is equal to x squared plus y minus 2 squared plus z minus 1 squared, subject to the constraint the x take away 2y plus 3z must equal 9. Right? That's our constraint function. Now, we're going to do exactly what we did the last time, right? But I'm going to do a little rearranging. If x take away 2y plus 3z is equal to 9, then 3z is 9 take away x plus 2y, and therefore z is going to be 3 take away 1/3 x plus 2/3 y. Are we good with that? Which means this equation doesn't actually have any z's in it anymore. It's going to be x squared plus y take away 2 squared. And instead of z take away 1, I'll make that z and I'll take away 1. And if I do that, I get 2 take away 1/3 x plus 2/3 y all squared. So basically, don't I just have a function with x's and y's in it?
Where'd you get the 2 at?
Where did I get 2? I said z take away 1. This is z
understand.
take away 1, which turned that into a 2.
Thank you.
Right. Now, I'm after the minimum value, right? The smallest answer. It has to happen at a critical number, and there has to be one. And because of that, our work rate is going to actually get reduced rather than bigger. I am going to look for critical numbers. And I am going to find just one of them, because there's only one. So that must be the answer. Right? So let's see if that happens. If you take a partial derivative with respect to x, this guy gets you 2x. I left this guy alone. I could have foiled him out, but I didn't bother. Would you agree that the derivative with respect to x is 0? Because there's nothing in here with x's. Now, this is a little bit messier, but it was worth it. I'm going to do the chain rule on this, right? Something squared. So it's going to be 2 lots of this guy to the power of 1, which I shouldn't really write, times the derivative of the inside function with respect to x, which ends up being -1/3. So this becomes 2x minus 2/3. And again, you probably don't need all these lines. It's going to be 2x. That times that is going to get me -4/3. That times that is going to get me plus 2/9 x. And that times that is going to get me -4/9 y. And then I'm going to take that guy and combine them together. And that's 18/9, so that's 20/9. Take away 4/9 y, take away 4/3. And that has to equal 0, doesn't it? So there's my first equation. I need to find out a value of x and y where this is equal to 0. And now I'm going to do essentially the same thing again, partial derivative, but with respect to y. So that'll get me nothing. This guy here will get me 2 lots of y minus 2 to the power of 1 times the derivative on the inside, which is 1. So I probably didn't need those ones now. Plus chain rule on this guy. 2 times this, what? To the power of 1 times the derivative of the inside function with respect to y, so it's times 2/3. This guy is 2y take away 4. This guy is 4 take away, it's not 4. Forgot my 2/3. Caught myself on time. So 2y take away 4. 2/3. Let me check something. Yeah, 8/3. that times that, -4/9 x, that times that, plus 8/9 y. There we go. And a little bit tidying up, not much. What can I get? I can get an x, so it's that guy. So it's -4/9 x. I got this guy and that guy. That's 18 plus 8, so I make that 26/9 y plus 8/3, and that also has to equal 0. And that is our second equation. So I now have to solve a system of equations. So I'm putting them both together now.
Hey, Mr. Robertson, what happened to the -4 term?
Where is the -4? What negative?
In 2y minus 4 plus 8/3.
Yeah. Okay, you tell me when to stop. Is it happening on this line?
No,
This one?
no.
This one?
Yes, that's the last time we see the -4.
This -4 here?
No, you have 2y minus 4 plus 8/3.
Right. Oh, I've got an 8/3 and a 4. There, you caught it. Yeah. So that guy there needs to be fixed, doesn't he? So what do you get? You get 12 add 8 is 4/3. So there we go. So if you take the number -4 and add 8/3 to it, I believe you get -4/3. And these are going to be equation 1 and these are going to be equation 2. Now, remember our goal here is to find critical numbers. So aren't we trying to find the value of x and y where these are true at the same time? These are decidedly ugly fractional expressions, and I'm assuming I didn't screw up. And no, I didn't, so that's good news. But they're still decidedly ugly. And there are two approaches to dealing with questions that have ugly values. And the first one is just live with it. And the second one is get rid of them. Do you want me to solve this question by just living with the ugly fractions, or do you want them gone? I mean, you're going to get the same answer. It's just I want to see how you want to proceed here. Do you want these fractions to all disappear, or do you want me to just go, oh, got a nod on it. Okay. If you want to make these fractions disappear, multiply everybody by 9. In which case you get 20x, take away 4y, and -12 equals 0. If you want this one to look nice, multiply everybody by 9 again, and you get -4x plus 26y, and 3 3s, that gives me take away 12 equals 0. Would you agree these equations are a little bit nicer to deal with? It's not that the method's going to change, they're just nicer to deal with. And I could solve this by the addition method or by the substitution method, right? Way back in the day when you did systems of equations. And the way I'm going to fix it is I'm going to multiply this guy, all of it, by 5. So I'm not going to do anything to equation 1. I'm going to multiply everybody here by 5. So there's my new equations. And now I can add them. And this guy becomes 126y, and this guy becomes -72, and this guy becomes 0. And I now have 126y is 72, which makes y 72 over 126, which I certainly don't like, but here goes. 72 divided by 126, make it a fraction, and the answer I get is 4/7. Wow, that's actually not bad, right? Could have been a lot worse. Now, if you know y is 4/7, how do I find the x coordinate? Think
Oh,
back to
boy.
Math 99. I know it's a long time, but how do I get x?
And
We can't remember, can we?
Substitute the 4/7 in for a y value in one of the original 1 or 2 equations.
Right, whatever one you feel like, really, doesn't matter, right? So I'm picking this one here because it doesn't matter. 20x, take away 4y, take away 12 is 0. So that becomes 20x minus 16/7. Yep, minus 12 equals 0. That makes 20x. Well, if you combine them and then push it over the other side, what do you get? You get, oh God in Himmel, why don't they have nice numbers? 84, add 16. Okay. Would you believe it? It's 100/7. That means that to get x, you just divide everybody by 20 and you get 5/7. And so there is only one critical number and its value is 5/7, 4/7. So that guy is actually the coordinates of Q. Now, if they wanted to know where on the surface was the shortest distance, you would say there. But they wanted the answer to D, right? What that number is. So if I put here P again, oh, where is it? I got my darn thing. Oh, here we are. I've got the formula for D. Which is him. Now, this formula that I've got here was D squared. So I'm trying to get all my bits of paper to the road. So I know that X is 5/7. I know that Y is 4/7. I know that D squared is equal to X squared plus Y take away 2 squared plus 2 take away 1/3 X plus 2/3 Y squared. And won't D then be the square root of that horrible mess? And I am not going to do that. I'm going to tell you what the horrible, do they ask even? Oh, I take it back. I'm pretending I know the answer to this. This is not true, but can you imagine the answer ends up being that? What they did ask you for in this question, let's check if they didn't do it for the others as well. No, they asked you for the coordinates. Oh, even easier. Q is X, Y, Z, right? That's the guy on the surface. We know X is 5/7. We know Y is 4/7. All we need to do is find Z, and Z was this guy. So Z is simply 3 take away 1/3 of the X coordinate plus 2/3 of the Y coordinate. And so Z would be negative 5/21s plus 8/21s, which is 3 add 3/21s, which is a 7th, which is 28/7. Bingo, we got it. Now, if they'd asked me to find the shortest distance, then this is the formula for D squared, right? In terms of X and Y. And I would have plugged in that number for 5/7, this number for 4/7, and 5 minutes later, got the square root of 17 or whatever it really was. But since they asked us for the coordinates of the point that's closest, we already know the X and Y. I found the Y by the rearranged version of the equation of the plane, plugged in the x and y, and boom. And I said 28/7, didn't I? How about 66 in this case? Oh, it is 28/7 if you simplify. Okay, I was right the first time. $20-odd minutes for one blinking question. Share a story with you once. I was doing one of, I remember this one because this is the kind of thing that you do remember. I was doing a question when I was at university, one of these, not this particular one, but something else. And it took me over 1 hour from start to finish to do the question. And it's not like I was spending 20 minutes thinking about it and trying 2 examples and changing it. It literally can take 1 hour to do one question. And the more advanced the math gets, the number of questions gets reduced, right? But the more time you spend on each question increases, right? So I think we're beginning to see the sign of it here, aren't we? Beginning to see questions that can take you 20 minutes. Maybe 15 if you cut out me talking. So be prepared to start your homework early. You're just not going to get through them if you don't. Now, we're moving on to our next section, Lagrange multipliers. Here we are. And it's the same questions that we've been doing, but a totally different approach. When you see the math here, you're going to say, well, that doesn't look much like what we've done, and you're right, it doesn't. Suppose you want to find the absolute max and min of a function, z equals f of xy, subject to some constraint, g of xy equals 0. So this here could have been 4x plus 10y minus 42 equals 0, right? Some constraint. It can also be a constraint where it's less than or equal to and all the other combinations, right? And this here is the function that you're trying to find the max and min of. Then how do we do it using these guys called Lagrange multipliers? By the way, that letter there is delta. It's a Greek letter, delta. Lambda, I should say. Lambda. A bit like saying lamb, sticking a dot at the end, lambda. And you end up having to solve this equation. And when you solve this equation, the values of x and y that you get out of it are the critical points. You know those guys that we did the other way, right? When f of x equals 0, f of y equals 0, and tried to solve some really horrendous equations. Didn't some of them end up pulling your hair out, right? Well, what we're going to do now instead is we're going to solve the gradient of f is lambda times the gradient of g. And when we solve this equation, which typically is a lot easier to do, although it's a system of equations, the answers you get are critical points. And then all you do is you evaluate this function at the 1, 2, or 5 critical points. And the biggest answer is the absolute max, and the smallest answer is the absolute min. So that's the big picture. That's how we are going to solve max and min problems using these Lagrange multiplier guys. So let me show you one. And I hope once you've seen it, you will say, I like this method better than the last one. So here is a function we want to find the max and min for, absolute max and min. And it's subject to the constraint that x squared plus y squared has to be equal to 16. Okay. Now, the gradient of f has to equal lambda, the gradient of g. Now, the equation for g comes from the constraint. Now, you can call the equation x squared plus y squared. You can also call this equation x squared plus y squared minus 16. Technically, you should call it that guy, because over here isn't g of x equals 0. Do you see how they write the constraint in that format? So you take the constraint and you use it like that, okay? But actually this works. And the reason why these two work is, aren't these two gradients the same thing? Because the number doesn't affect the gradient. So let's see what we get. The partial derivative of f with respect to x, partial derivative of f with respect to y, is going to be lambda, the partial derivative of g with respect to x, and the partial derivative of g with respect to y. This is my f of x function, so I get 2x and negative 2y. And by coincidence, the constraint function looks very similar. This guy is 2x and this guy is 2y. So far, so good. Now, what I'm going to do is basically break this into a system of equations. So if you match this guy with this combination, 2x will have to equal 2 times lambda x. Are you good with that? Now, if you match the second value, which is this and this, you get the relationship that negative 2y has to equal 2 lambda y. And I'm going to call this equation 1 and this one equation 2.
Oh, sorry. How did you get the 2x is equal to 2 lambda y?
I matched this guy with the first one of this guy, and this guy with the first one of that guy. If you need an extra line, it might look something like this. And I'm just saying the two first components are equal and the two second components are equal. You see it now?
Yeah, thanks.
Okay. Now, you're pretty much guaranteed the way that this is constructed, aren't you, to get two equations, right? And they're going to have an x, a y, and a lambda in them. Typically, that's what a little line there is distracting me. That the way you solve these is not a typical process, but it is very consistent. In other words, you kind of do them all the same way. So first thing you're going to do is you're going to assume that lambda equals 0. Right? And you're going to then find out what solution comes out. If I make lambda equals 0, won't 2x be 2 times 0 times x is 0? And won't negative 2y be 2 times 0 times y, which is 0, which means I get a x equals 0 and a y equals 0, right? Now, I'm not going to call that a critical number yet. I'm going to call that a potential critical number. How do I know if it's usable? You take that and you go back to your constraint. Me personally, I like the constraint function in that format, right? X squared plus y squared equals 16. Now, if x is 0 and y is 0, does that match the constraint? Is 0 squared plus 0 squared 16? No, which means you can't use me as a critical number. Okay, now 9 times out of 10, you never end up using the assume lambda equals 0 solution, right? The point that comes out either doesn't exist, right? There's no solution possible. Or you get a solution, but it doesn't match the constraint. But I'll tell you, this is Murphy's Law. See, the one time you didn't do it is the one time where it is actually one of the critical numbers and you should be using it, right? That's Murphy's Law. So you're going to keep doing these and you're going to do like every single question and you're going to say, oh, come on, I never end up using them. Why am I spending my time finding them, right? I bet you the next question where you decide not to do it is the one you should have done it and you end up getting it wrong. And that's just pure Murphy's Law. Well, once we've got the assume lambda equals 0 out of the way, which is part of this process, you can now assume that lambda is not 0, which kind of makes sense. right? I've already checked for lambda 0. Let's assume that lambda is not 0. And again, I'm taking this one nice and slowly. There's my equation 1 again. Here's my equation 2. And what you do is you take equation 1 and you take equation 2. Right? Divide them. Right? Haven't we had questions where we've added them together, right? I don't think we've done one where you divide them. Let's see what happens. On the left-hand side, you get that. On the right-hand side, you get that. So far, so good, right? Equation 1 being divided by equation 2. Now, if you simplify this, you get x over negative y. And if you simplify this, you get x over y. So far, so good. Now, at this point, you are trying to solve. Now, what I mean by solve here is not find x equals a number, but just find something like y is 2x, or y is a half x, or y is x squared, right? You're trying to find y in terms of x, or sometimes it's easier to find x in terms of y, but that's what you're trying to do. If I cross multiply these, don't you get xy is negative xy? In this particular case, you get that. And just to prove me wrong, but most of the time what I said is correct, this one has got a little twist on it. I'm going to solve it. There are going to be two cases. And these guys are going to generate potential critical numbers. You remember that potential critical number never made it. Now, I know 0, 0 doesn't work, right? But x equals 0 might work, right? Let's see what it looks like. If you go to the constraint function and you say, if x is 0, what values of y might work? Can you see that the values of y are plus or minus 4? Which means I have 0, 4 and 0, negative 4 as two critical numbers. Now, what about y equals 0? Well, if you return to the constraint function, as you always should, you get x squared plus nothing squared equals 16. This is kind of deja vu again. This is x squared equals 16. So this gives you plus or minus 4. And so we have 4, 0 and negative 4, 0. Now, in a lot of the cases, what you end up here with is y equals x squared. Now, if you did end up with y equals x squared, which is what I thought was going to happen here, you would still do the constraint function, but wouldn't you replace that guy by whatever y is equal to and solve for x? And that way you'd be able to get your constraint functions that way. Now, there are 4 critical numbers. And they are 0, negative 4, 0, 4, 4, 0, and negative 4, 0. And for each one of them, we evaluate the original function, not the constraint function, but the original. Right, if you plug those numbers into here, the value, well, I'm not going to write that all the time. The value of this is going to be negative 16. If you plug in this one, it's also negative 16. If you plug in this one, it's positive 16. If you plug in this one, it is positive 16. Here is our answer. The absolute minimum value that this function takes is negative 16. And the absolute maximum value that it takes is 16. And that question took me 15 minutes. If I tried it the other way, wouldn't it have taken 20 minutes? At least, I think. And that is us using Lagrange multipliers. I've got time for another one. Let's see if I can find one a little bit messier than that one. That's pretty, oh, is that straightforward? It's hard to tell, hard to tell. Hard to tell. Okay, I'm picking 3. It's difficult for me to know when I'm looking at that question there, what kind of, what's going to happen in the math when we solve it, what kind of things are going to turn up. But here, anyway, here's our constraint function. Okay, I'm just going to use that as the g of x. Okay, so the gradient of f is lambda, the gradient of g. Partial derivative of x and y of f, lambda times partial derivative of g with respect to x and y. If you differentiate this, you get y. If you differentiate with respect to y, you get x. If you differentiate this constraint function, you get 32x, and do it with y, you get 32y. Oh, I can see what's going to happen here. That's fine. It's going to look very, I think this one's going to look very like question 1. Let's see what we have. Y is going to be 32 lambda x, and x is going to be 32 lambda y. Oh, okay. Now, there are 2 situations. Assume lambda equals 0. Right. And it's not going to work. Can you trust me? I'm just going to tell you it's not going to work because I want you to do this quickly, right? If you assume lambda equals 0, you get x equals 0, y equals 0. Does x equals 0 and y equals 0 satisfy the constraint function? No, it's not equal to 32. So that gets kicked out. So I'm breaking my own rules for time purposes. I'm going to assume that lambda is not equal to 0. Then I should take equation 1 and divide it by equation 2. So I get y over x is 32 lambda x over 32 lambda y. Are you good so far? Have you noticed that every single time that's what we do once we've got rid of the lambda equals 0 situation, right? Now you can simplify that a little bit by cancelling all the 32s and lambdas and getting that. And then you get that relationship, which is the one that's more typical. So y squared equals x squared is a relationship that we can use. Okay. Now, I'll start up here. Does it not make y plus or minus x? Would you agree? So that gives me 2 scenarios to check. If y is equal to negative x, the constraint function says that, agreed? And if y is equal to negative x, we have x squared plus negative x squared is 32. We have 16x squared plus an x squared is 32. We have 17x squared, which is still 32. And x squared equals 32 over 17. Well, that means that x will be positive the square root of that guy, and it will be negative the square root of that guy. And I wish they'd gave me questions which are nicer, but they didn't. But I can make that 4 root 2 over root 17, And I can make this negative 4 root 2 over root 17. I don't think there's much benefit, but I do have some critical numbers. X is 4 root 2 over the square root of 17, and the y value will be the negative of whatever the x is. So you have negative, that guy. The other possibility is that this would be a negative number for x, and since y is the negative of what x is, you get a positive value for that. Are you comfortable about where those two critical numbers have came from based on the working that we've done here, right? We replaced the y with negative x, and we ended up with an equation with x's, which when we solved gave us two solutions. For this solution then, the y will be the negative of it, so that's 1 point. For this solution, the y will be the negative of it, and it's that one. And then you have another possibility that the y and the x are the same thing. And if I did that, would you agree that you virtually get exactly the same working? Try to speed up things here. So you would end up with 4 over root 2 17, or negative 4 over root 2 square root of 17, which means that there are two more solutions. X is that guy, and y is the same guy. And x is the negative of that guy, and y is the same as the x value. So we have 1, 2, 3, 4 critical numbers. So to finish this question, we would probably set up a table of the x, y values, and we'd evaluate the original function, not the constraint, but the original, at those points. So if you type in this one, for instance, 4 root 2 over the square root of 17 and negative 4 root 2 over the square root of 17, and you multiply those two together, actually, oh, isn't that nice? That the answer you get is negative 32 17ths. And if you put that one in, where they say both negative, you get positive. And if you put in, first one is negative, and the second one is positive, you get that guy again. These are kind of random order, but I'm putting them all in, so it shouldn't matter. And there's the fourth one of the choice. And in that case, you get that. So everything we need is here. That's your absolute minimum value. Negative 32 17ths, and it happens at that point, and it also happens at that point. And these two guys here, they're the absolute maximums, right? And they happen at this point and at that point. So if I put this equation into Desmos, and I could find a way, which I don't know how to, but find a way to make this a constraint, and it wouldn't be Desmos, it would be GeoBra. If I put this into GeoBra and put this constraint on it, I would find out that the highest the function ever got to was this value, and the lowest z would be this value. It's still a long question, agreed? In a way, isn't a lot of what you do repeating yourself? You're just doing it and then you get a similar answer, and then you do it again, you get a similar answer. But it has a flow to it, which I think helps, because if you were doing it yesterday's way, don't you have to find unique ways to solve equations? Because each one's a little bit weirder than the last one, and you have to figure algebra ways to do it. In this case, isn't the algebra a little bit easier? You divide the equations, you'll get some relation with x and y in it. And then whatever that relationship is, you plug it into the original, you plug it into the constraint, and that's where the critical numbers are. And once you know your critical numbers, then you plug them into the original function to find your max and min. Is it possible for me to do a question where there's only absolute minimums, but no absolute maximums? Let me phrase it a different way. If you take a function, but you put a constraint on it, so you only look at a certain place, is it possible for you to have an absolute max and an absolute min? Yes, we find them. Is it possible not to? And the answer is correct. I'm totally useless at drawing these things, but I'll do my best. Can you imagine a function that looks like this? And in fact, that would be a bad choice. Looks like this. There we go. At the point -1, 1, won't this function have a problem? Won't that problem be a vertical asymptote in at least 141 world? What does a vertical asymptote look like in a 3D world? It looks kind of like that. Can you imagine a spout getting thinner and thinner and thinner and zooming off through the roof? Can you see that a vertical asymptote in 3D kind of looks different? Now, that's not the only kind of vertical asymptote. You can get vertical asymptotes that look like this in 3D. Can you imagine two curved planes coming up vertically? Like two pieces of paper meeting on a line, right? So couldn't you have an entire line of vertical asymptotes? So in the 3D world, it is possible not to have a max, an absolute max or an absolute min within a certain constraint. So what on earth does that look like? When you try and evaluate one or more of these guys, you end up with this. Won't you end up with a 10 divided by 0 kind of thing going on? And if you see that, doesn't that mean no absolute max? Because that's infinity. Right. So if you, I don't think any of the questions did this, thank goodness, but if they did, couldn't you get a situation where there was no max and mins? In fact, couldn't all four of these be different versions of, you know, it ain't happening? Wouldn't that be an example of no max or min? Right, that'd be a really weird, horrible function, but theoretically it's possible. I can tell you right now, if I do a quick look at the solutions, everything's good. There is not one question that has a vertical asymptote in it. So all your answers are going to have a max and a min, right? So you know that they're out there, you're just going to have to find them.